my point of departure is this, that in our industry does a lot of reservoir simulation and modeling. That's the basis for all reservoir management. But what I submit to you is that we do not take full advantage of all that a numerical reservoir simulation model that has to offer. We barely scratch the surface. Why? Very simply because it takes forever to make a run. When it takes 10 hours to make a run, when it takes even 1 hour or 45 minutes to make a run, forget about doing exhaustive analysis, because for that you need millions of runs and you never can do it. Return on investment on numerical models can increase significantly if you use SRM. SRM is a highly accurate replica of traditional numerical reservoir simulation model. Reproduces the results with 95 to 98% accuracy, with one difference. It does it in real time. Now, if you want to do smart field analysis for a smart field, reservoir analysis, probably you should look into this. Real time. So I'm going to show you one case study. It's a giant oil field in the Middle East. The concern was the water production was becoming a problem. Wells are restricted in terms of their production in order to avoid bypass oil and early breakthrough. And the reservoir model includes a lot of uncertainty like any other reservoir model. So the technical team wanted to identify the fact that they believe that there are certain wells that they can produce a lot more oil if we reduce the restriction on usually their flow choke it back, so it will not flow as freely as you want, because you're injecting water and water takes the path of least resistance and can break through early. So that's why they choke it back. But the engineering team says, no, there are wells that we can actually open without having any problem of water breakthrough. So the challenge was to identify out of 165 wells, which one of these wells will not suffer from high water cut once you open the choke or relax the rate, and which one will. The solution is to comprehensively explore the solution space while quantifying the uncertainties associated with the model. It required hundreds of thousands and literally millions of simulation runs. But there was one problem. I had 165 wells, 1 million grid blocks, and it took 10 hours to make a single run with a commercial reservoir simulator that everybody is familiar with on a cluster of 12 CPUs. Making 1 million run would take about 125 years. So we built an SRM. The input to SRM was 500 potential parameters. The output was the oil, water, cumulative production, and instantaneous water cut. After we finished our analysis, this well, we told them this ranked number 1. We told them, go open the choke on this well. You are going to produce millions of barrels of oil through 20 years without any water problem. They ranked it number 1. This well, we said, don't touch it. You open the choke on this well, you're going to water it out very, very quickly. So at the end, we took the 165 wells and divided into 5 clusters, 1, 2, 3, 4, and 5. And we told them, open the choke on cluster 1 and cluster 2 wells. Do not touch cluster 4 and 5. And cluster 3 could go either way. They did it. After 2.5 to 3 years of actual production, they tested all 5 cluster wells, the wells in all 5 clusters. And what you see in the next couple of slides are no longer simulated results, but actual results. Actual field data. So here you see cluster 5. These are the wells we told them don't touch. The green here is water cut. In every case, as soon as they relaxed the rate, the water cut increased. That was what we predicted. These are cluster 1 and 2. These are the well we told them, go ahead and open the choke. You're not going to have any problem with water. In every case they did that. That was the result. As you see in green, the blue shows you the increase in production of oil, but the green shows you reduction in water cut. In other words, out of 20 prediction, every single one of them came true. So what you see here, the maximum amount of water cut in each cluster, normalized for number of months and number of wells, before rate relaxation and after rate relaxation. Before and after, before and after, and as you see. So that was, who should get credit for that? People who built the reservoir simulator. Apparently the reservoir simulator was quite accurate. But the problem is, in order to get this result, you needed to run the model 1 million times. Once you run it 1 million times, it gives you incredible, fantastic results. But because we only can run it a few times, it may not necessarily return the investment that we put in it. A second case study. The objective was to build surrogate model for green fields here. Some of these fields are up to 6.4 million grid blocks. Now, all I'm going to show you, really, is how heterogeneous these reservoirs were. This is not a simple case. Very, very heterogeneous permeability and porosity, as you see. And what I'm going to show you is the result, is what SRM did, our surrogate reservoir model, versus the actual reservoir simulator from the NOC. It's practically on top of each other. The difference is the SRM runs in real time. This is for entire field. You have rate versus time, and you have cum versus time. SRM and the simulated system. This is for wells on top, wells in the middle, wells in the bottom, and you can actually see a single well. And then we can actually perform in real time, in fraction of a second, we can perform, we can quantify uncertainties associated with the reservoir simulation model and how does it impact the Q1, let's say, after one year. We can get P5, P95, and P50. So then we go and test it on one of the runs. The beauty of SRM is this. This is not response surface. You do not need thousands of runs in order, or hundreds of runs in order to build a response surface. The one I showed you before took only 10 simulation runs. This one is taking only 9 simulation runs for us to build it. This is a 10 completely blind simulation run with characteristics that was never seen by artificial neural network system that we use as part of our SRM. Completely blind data set. Run, simulation run. But look at the accuracy. Once it's trained offline, you can put it online, and it can replicate with very, very high accuracy the results of your reservoir simulator. The difference is it does it in real time. Single well. This is oil and gas for that well, oil and gas for another different well. Now, I can do that. Now, what I'd like, some people compare this to response surfaces, but response surfaces cannot do that when it comes to grid, giving you results at a grid-based level. Here, what I'm going to show you is change of saturation from this field. The cross sections are I. So what you're going to see are I versus J in I cross in K, I versus K, J versus K, and I cross sections. And here's the result. What you see on the top is change in saturation from a reservoir simulator, and the one in the bottom is the same thing replicated by SRM in real time. To see how close we can replicate what you see in the reservoir simulator, we just do it in real time. So with that, I got only 4 minutes. So let me show you some results from top-down modeling. Remember, SRM, I got my data from reservoir simulator. I just cranked it. It's a reservoir simulator on a steroid. Take your reservoir simulator, runs it in very, very fast. Now, this one is top-down modeling. What top-down modeling is has absolutely nothing to do with reservoir simulation. It uses no interpretation, no geological model. Everything comes from the actual field measurement. So what if we let the reservoir and well speak for themselves and just learn to listen and listen well to the reservoir? TDM is a reservoir simulation model that is built purely based on available historical data measurement, no assumption, no interpretation whatsoever during the construction of the model. This case study that I'm going to show you real quick is a giant field in Middle East. The numerical modeling effort on this is taking many, many years and still not completed. We completed the project in 9 months. The challenge was to history match all the wells and for all the formation that was proved to be a nightmare in reservoir traditional simulation model. So what I'm going to show you is, first, the top one. I'm going to show you the match for the entire asset. Then I'm going to show you for 5 separate units, one at a time. Then I'm going to show you for each well, which is completed in multiple unit, multiple formation. Then I'm going to show you every string in every formation very quickly. So that is the only thing that you should remember. We had data from 1975 to 2010. We built our model and history match it from 1975 to 2001. From 2002 to 2009, our match that you see is completely blind. That data was not used during the model development. And then 2010 to 2014 is forecast. So what you see here is for the entire field. This is rate versus time. And the shaded area is completely blind. The rest is history match. This is the same thing, and the bottom is cum versus time. Again, this part is completely blind history match. This is the entire field. This is completely the entire unit 1, the entire unit 2, the entire unit 3, unit 4, and unit 5. Now, on a well-by-well basis, this is a well that was completed in 3 formations. A well completed in 4, in 3, in 2 different formations. And now here is where we actually built our model at, string by string. And you can see the shaded area is completely blind history match. And for this particular system, since we had some water saturation history, we could actually go to the grid block level and identify the water is being injected at the periphery, and it's a water drive. So you can see where we can tell where the water is actually going and match it with the historical water saturation, time-lapse water saturation logs, and the pressure as well. So the conclusion. We have introduced a new reservoir modeling technology that uses pattern recognition capabilities of artificial intelligence and data mining. AI-based reservoir models technology attempts to construct reservoir models based on a representative, a spatiotemporal database, not based on first principle physics and math. Examples of AI-based reservoir models were shown that apply to real life. When the when the data comes from real field, we call it top-down modeling or TDM. When it comes from simulated data, we call it SRM or surrogate reservoir model. And thank you very much for your attention.